Hello again, guys. I'm going to start today a problem which is fairly common. This problem is fairly common in shear moment diagrams, and the problem is about a triangular load. That's it. I'm gonna try to do this problem explained by using the three methods: the method of the sections, the method of the integrals, and the method of the areas. So let's start by doing this problem by the method of the sections. There is a way of starting this without even calculating the reactions, but it's well, not in this case. This case we have to calculate reactions, some of the cases, but I always advise you in these type of situations to start by calculating the reactions. So the first step is recognizing the reactions, and this is like always. This is a pin, this is a roller. This is going to produce two reactions, but I can see immediately that AX is 0 because there's no horizontal force. And I'm going to call this AY, and this is going to be BY. So if we want to calculate the reactions, we're going to say summation of moments at, I can do moment here, at B equals 0. So if we do summation of moments at B equals 0, then we have that, and I'm saying that counterclockwise is positive. So we can say that AY times 6 in this direction, clockwise, is negative. And there is going to be a force coming from this triangular load, which is 42 times 6 divided by 2. Remember, this is the area. The total load coming from there, 46 times 8 divided by 2. And the location from this point is 1/3 of the base, which is 6. And it's positive because it's acting in this way. So negative AY times 6 plus 48 times 6 divided by 2, that's the force, multiplied by 1/3 of the base. And I don't have anything else, equals 0. And from here I can immediately say that AY is going to be, let me see, this 6 and this 6 cancel out. This is actually 6 and 3 is 2, and this 2, this is 48, 48, 48. And I can do, if I want to, summation of forces in Y equals 0, and then you have AY, which is 48, minus this force is 48 times 6 divided by 2, plus BY equals 0. So BY is going to be this difference. This is 3 times 48 minus 48, this 2 times 48, pass it to the other side. So BY is going to be 96. Okay, now we have the reactions. We can start by doing the method of the sections. If I want to calculate the section in this method and doing the method of the section, what I'm going to do is I'm going to apply a section at an arbitrary point here. In that section, this distance from here to here, it will be called X. And I'm going to reproduce the same drawing here. This value is AY, 48. This is my force coming in this direction. I don't know how much is this height for this triangle, but I can know it because if you realize this is the equation of a straight line. So basically the equation of a straight line, remember, y equal mx plus b, where b is the y-intercept. The y-intercept here is 0 because it's the point where that line is cutting or intersecting the y-axis, and the slope is going to be 48 divided by 6, so that means that the slope is 8. The equation of this line is 8x. That's going to be the equation of that line, which is going to be also this height at any point. 8x. And remember, this distance is x, and at this end, because we are doing the section and we are studying this side, I'm not gonna get tired of saying that to you every time. So we are gonna use this convention, V and M. And remember, I am not copying the x, the axial, because in this case we started with the axial equals 0 due to the fact that there's no horizontal force here. Okay, so then we can do summation of forces in y equals 0, and if we do summation of forces in y equals 0, then we have 48 minus v minus the force that comes from this triangle. Remember, the force that comes from that triangle is no other thing than the area of the triangle, and this is 8x, the height, multiplied by x, the base, divided by 2. And the location from this end is always going to be from the right angle, 1/3 of the base, which is x. So if I want to calculate the force is going to be 4x divided by 2, which is 4x squared. So I'm going to copy here 4x squared equals 0. And V, which is the shear, is 4x squared negative plus 48. That's my equation for the shear. Now we can do the evaluation of the shear and how much is the shear for x equals 0. And remember, x is going to go from 0 until 6. So for x equals 0, I can calculate V of 0, which is negative 4 times 0 squared plus 48, meaning V of 0 is 48 kilonewton. I'm not pointing at this because it's 48. I'm just pointing at the units, kilonewton. And for x equals 6, which is at the other end, then we will have V of 6 is negative 4 times 6 squared plus 48, and V of 6 then is negative 96 kilonewton. 96 kilonewton. Now, once we have the shear, we can either plot the shear or go to the moment. I like plotting the shear once I have it. I'm going to plot it here. So remember, the way I do this, and I always tell you this, you draw a horizontal line, a vertical line at the beginning of the section, at the end of the section, and wherever you have any other interesting point or points of interest. And points of interest, I define them as any place where you have a concentrated load, a concentrated moment, when you have a support, when the load, the distributed load begins, when the distributed load ends, or in some situations, if you have difference in the sections, let's say the section here is a 2x4 and then the section here changes in 4x4, that would be also a point of interest, which it doesn't apply in statics, by the way. In statics, it's only at the beginning, at the end, and wherever you have concentrated loads or beginning of loads. In this case, it's only 2, and then I draw a horizontal line, and here I'm going to draw my shear diagram. Now, at the beginning, we always ask and have to ask ourselves the following question. I always tell the students to do that. Remember, AY is 48 kilonewton, and this value BY we calculated as negative 96 kilonewton. So the question that I ask you to ask yourself is, do I have any concentrated load at the point of origin? And even if I don't do that with the method of the sections, you can see that the value that we calculated, it was 48 kilonewton at V equals 0. That means that at 0, which is this point, I have to start with 48 kilonewton here. And this is a jump because it starts from 0 and goes here. And this is what is telling you this force. You see this force pointing up, that shear force pointing up is telling you that at this point, it's going to be a jump in your shear diagram because you have a concentrated load from 0 to 48. At the end, you have negative 96. For V equals 6, you have negative 96 here. Negative 96. Now, the question is how I go from this point to this point. Well, that is easy because you have the equation. Let me copy the equation here. V equal negative 4x squared plus 48. This is the equation of the shear. This equation is the equation of a parabola. And it's an equation of a parabola where the x squared coefficient is negative, meaning the parabola has to follow this shape. Now, this point here is a really interesting point, because in that point the shear is 0. And at the same time, as you are going to see and as we explained in class, at the point where the shear is 0, you always are going to have either a local maximum or a local minimum at the moment. So we have to know how much is this distance, because that distance is going to give me, that x distance here is going to give us the value for the maximum, local maximum or local minimum moment in this span. And as I say, if this is the shear diagram, at that point the shear is 0, meaning this has to be 0, meaning 4x squared plus 48 has to be 0, and I can solve x as I pass this to that side. 48 divided by 4 is 12, square root of 12, and the square root of 12 is 3.464 meters. That means that this distance at which the shear is 0 is 3.464 meters. That distance is important for you. Not for the shear is important because it's 0, but for the moment it's going to be extremely important. Now we have our shear. We go back to our diagram here, our section, and we are going to do then summation of moments. I like doing summation of moments at this point, at the moment of the section. Let's call that point B prime. So I'm going to do summation of moments at B prime equals 0. And if you do that, what are we getting? We are getting 48 times this distance from here to here. That's x. And it's going to be a negative moment. So 48 times x. And then we have this force, the vertical force coming from the distributed load, which produces a positive moment. The value of the load is 4x squared, and the distance from this end is 1/3 of x, plus this moment equals 0. There you go. If we solve this equation now, we have that moment is going to be equal. This is 4x cubed divided by 3, and it's going to be negative when I pass it to the other side. Negative 4x cubed divided by 3 plus 48x. That is our equation for moment. So we have to calculate the moment at the beginning and at the end. How much is going to be the moment at here? You have to realize that this is a pin, so the moment here has to be 0. If by any chance you put here x equals 0 and you don't get 0 as a moment, for moment of 0, then you did something wrong. Go back and review your equation. So for x equals 0, moment is 0. The other point that I'm interested in calculating is this other point here. At this point, I have to calculate the moment at x equals 6. The moment at x equals 6 is negative 4/3 times 6 to the third plus 48 times 6, and that is also 0. Does that make sense that it's 0 here at the moment? Of course it is. It makes sense. Why it makes sense? Because at this point there is a roller, and I'm not supposed to have any moment there unless I have a concentrated moment applied at that beam. So this is 0. The other interested point that I have, a point of interest that I have, is this one. So I have to calculate the moment for x equal 3.464, and that's negative 4/3 of 3.464 to the third plus 48 times 3.464. So the moment is going to be 3.464 at that location. The moment is going to be 110.85 kilonewton meter. As you can see, this is a moment bigger than the other two. So the moment is going to be plotted here, and at this point is 0, and at this point is 0, and at this point is 110.85. If you have this equation, which is your equation of the moment, you can put it in your graphic calculator, and it's going to tell you that the shape has to be something like this, with this is the maximum value here, and then it's going to come back to 0 here, something like that. Now, by the way, I didn't tell you this, but once you reach the shear here, 96, that we got in the equation right here, then you have to ask yourself the question again, do I have any concentrated load here? Yes, you do have one. What is the value of that load? 96, and that 96 is pointing up. So that means that this point is going to go up and it's going to close the shear in 0. So this is your first shear moment diagram for the method of the sections. Now, if I want to know how much is the shear at any point, I just have to get the value of x here, and that will give me my values for shear at any point. Same with the moment. I can put any value of x here and will give me any value of moment. Now this is the method of the sections. Let's do the same problem by using the method of the integrals, because I want you to see the difference between the several methods, and you have to learn all the methods. One method is going to be definitely more useful for one case than for other, and it's going to be easier also to use, in my opinion, but that's my humble opinion. The method of the sections is one of the longest and most difficult for most of the cases. So let's do the method of the integrals now for the same problem. Let me see if I have it here somewhere. Yes. So we have this. How do we start this problem? We start this problem in the same way. I put a line here, I put a line here, I put a horizontal line where I'm going to plot my shear, another horizontal line where I'm going to plot my moment, and we start calculating reactions. How do you calculate the reactions? Exactly in the same way that you calculated the reactions before, so I'm not going to do it. I'm just going to put the values of the reaction here. 48 and 96. Those were the values of the reaction. Remember, kilonewton and kilonewton. First thing that you do is, do I have any concentrated force or shear force applied at this point? And the answer is yes, we have. We have a concentrated force of 48. That means that if this starts in 0, it's going to go up in the same direction of the load up to 48. This is the first point in my diagram. Now, the second, remember the shear is going to be the integral of the load plus this boundary condition value here. This value is going to represent the value. Right now we are studying the span, let's say AB, for AB. So if this is for AB that we are doing, it's only one span, this C is going to be the value of the shear at A, meaning at the beginning of the span that I'm studying, read from the diagram. That means that that C is going to be 48. That value of C is 48, but that 48 is because I read this value. This is C for the first span, which is the only span in this case. Now the other thing that I need is my load equation. And pay attention to this, because this is the trick here. The equation of the load is just imagining this. This is the load, because this is a triangle. These are your axes, but instead of being x, y, this is x and this is w, because this is what I have here. And this is the shape of my load. Well, what I have here is this. This is 6, this is 0, this is 48. And if I say y equal mx plus b, or w, in this case, equal mx plus b, b is my y-intercept, meaning it's 0, m is the slope, 48 divided by 6, so my equation is w equal 48 divided by 8, by 6, 8x. This is my equation of the load, and this is what we are going to do the integration, exactly in that value. So my shear is going to be the integral of 8x dx. And this is the trick. I have to put a negative sign here, and the negative sign is because my loads, as you can see, are acting in the direction of the gravity. This negative sign I'm sorry about that. The thing is, I don't know what happened with the system and something went black here. Okay, I was saying this negative sign here happens because the loads, as you can see, are pointing downwards. And this is the only trick that we have to do. Plus my value of C, read from the diagram, 48. When I do that, my shear equation is going to be, this is going to be 8x squared divided by 2, 4x squared, plus 48. This negative sign affects only the integral, not this term. And this is my equation of the shear. Now you say, okay, for x equals 0, how much is the shear? 48 kilonewton. For x equals 6, how much is my V? It's going to be negative 4 times 6 squared plus 48. And that's negative 96 here. Because my equation follows a parabola with the coefficient of the x squared negative, this is going to be the shape. Do I need this point? Yes, of course I need that point. And how do I get that point? By making my shear equal 0 in this equation. Negative 4x squared plus 48 equals 0. X equals 3.464, and this is the value, 3.464. I go to this point, I say, do I have any vertical force going up? Yes, not vertical, but shear force. That means that this is going to jump in that point, and it's going to reach 0. And I always joke in class and I say, you say now yes. You say yes, you know, it's a quiet yes. Why is a quiet yes? Because if this closes in 0, that could mean that whatever we are doing is correct. It doesn't ensure that it's correct, but it tells you that we are going in the right track. Now, if this is not 0, definitely it's wrong. It has to close in 0 always, your shear moment diagram. So the shear closing 0. Let's see what happened with the moment. Now, moment. What is moment? Moment is the integral of what? Of the shear plus some value. That value is going to be the value of the moment at the beginning of the diagram. Moment. In this case was shear. In the case is moment, because what we are doing now is moment. The value of the moment at the beginning of the diagram, it has to be taken from the diagram. Now, we haven't started the diagram yet. Let's start the diagram. Look at this point. Do you have any concentrated moment acting in this way? In this point? And the answer is no. You don't have any concentrated moment because this is a pin and I don't have any moment acting on that point on the beam. If this was a fixed support, yes, I would have a concentrated moment. But this is a pin. So my equation or my diagram starts in 0. 0, meaning that C is going to be 0 because this is going to be my value of C for the moment in that point, for that span. And my shear is this. So this is going to be the equation that I have to integrate here. Moment is going to be the integral of that equation. And I don't put any negative sign like I did with the forces because it's already taken into account here. So I'm going to integrate negative 4x squared plus 48 dx plus 0. So the equation for the moment is, when I do this integration, this is going to be 48x minus 4/3 of x to the third. And this is the value, the equation for the moment. If I say x equals 0, moment is going to be 0. If I say x equals 6 or moment of 6, this is going to be 48 times 6 minus 4/3 of 6 to the third, and moment of 6 equals 0. Also ends in 0. And I need to know the value of the moment at this point. moment at that point, it will be moment of 3.464, and that is 48 times 3.464 minus 4/3 of 3.464 to the third. Once again, that value is 110.85 kilonewton meter, and that's the value of moment at this point. You can put here kilonewton, and you can put here kilonewton meter, and you don't have to copy every time the units. Now, how is the shape? Because this is a cubic equation, this is gonna follow a shape like that. And now we have our moment diagram. So we saw the method of the sections. Now we did the method of the integrals. The method of the integrals, which is this one, in my opinion, is a little bit shorter than the method of the sections. Now let's look at the last method, and the last method is the method of the areas. And the method of the areas is not anything different than we have been doing. It's just a different application, because if you remember, and you should remember, the definition of the integral is the area under the curve. So when we do the method of the areas, what we are doing basically is applying the definition of the integral. How do we start this? In the same way. We start this point, we start at this point, and then we put a line for our shear, we put a line for our moment. Remember, this is going to be kilonewton, this is going to be kilonewton meter. We calculate our reactions like always. And when we calculate our reactions, I'm not going to do it again, but we got 48 in this one, and we got 96 in this one, kilonewtons, of course. And this reaction in X is 0. This point we call it A, this point we call it B. And now we start doing the areas, and I would like to see something like that if you're going to use this method for solving any problem. I will start you with saying point A. And at the point A, then you say, okay, at point A, there is a force going up, and that force is 48 kilonewton. That means that my shear is going to be 0 plus 48 equal 48 at that point A. 0. And then I find a force pushing it up, 48. I push my diagram up to 48. This is the same beginning that we did with the method of the integrals. Exactly the same. Now, here's where the fun starts. Then I go to the span AB. And then you say, I started my span with 48, which is this value here, and then I find this triangular load on top of that. That triangular load, first of all, is negative, because it's acting downwards. It's negative, and it's a triangular load, right? That triangular load, the value of that triangular load is the area of that, which is 6 times 48 divided by 2. So I started at this point, and I subtract this area. The value for that area, when I subtract 48 minus this, is going to get negative 96. So that means that at the end of this span, I'm going to get a shear of negative 96. And because what is happening here now is that this is a triangle, what I'm going to have here is a parabola. But I want you to learn this method that I'm going to explain you. It's an old school method. And I want you to learn this little mnemonic device. And I did a contest in my classes to see, like, please excuse my dear Aunt Sally for PEMDAS for parentheses, exponent, multiplication, division, addition, and subtraction, order of operations. I did like a little mnemonic rule for this. My students, only one student came, and I haven't found any. So if you find some, please email it to me. And this student say, in order to remember this, that student say, please don't neglect infants. Neglect, dumb people instead. And these are the letters PD and I and D and PI. And what those letters mean is positive decreasing, positive decreasing, negative increasing, negative decreasing, and positive increasing. What does that mean now? Well, that circle is going to tell you the shape of the shear and moment diagram. And the way you use it is like that. The type of curve that I'm gonna use to join these 2 points is defined by this circle, but I have to study the area of if I'm working with the shear, I have to look at the load. If I'm working with the moment, I have to look at the shear. So in this case, I'm working with the shear, I'm going to look at the load. And then I say, okay, this area, first of all, is positive or negative? And the answer is negative. Why? Because the arrows are pointing down. It's a negative area. So that area, this area, is negative. Now, I know it's negative. It could be increasing or decreasing. The only thing that I have to do now for determining the other letter is I cut a piece of area here, and I cut a little piece of area of the same size here, the same width, and I see just the height. If the height is increasing no matter the sign, then the area is increasing. Meaning it's negative because the arrows are going down, and it's increasing because the height is increasing. So it's negative increasing. Negative increasing says that it should be like that. That means that this is the shape that I'm going to use for joining those points. Exactly that shape. And then I go to this point and I say, okay, do I have any concentrated load acting up? Yes. How much is that? 96. This is negative 96. 96 up, 0. And you say, yes. And for the point B, I want to see here, well, of course here I have to see negative increasing for the shape. And you can put here parabola, just to know that it's a parabola, because from the triangle comes a parabola. And it's negative increasing. Negative increasing is because of this. And at the point B, you have negative 96 plus a force of 96. That's going to close in 0. Done. You see how many calculations we did here compared with the other ones? None. I spent some time explaining it, but calculation-wise, we haven't done anything yet. Now, for the moment. And for the moment, we do the same thing exactly. We start from this point and we say, okay, what is that point? Do I have any concentrated moment here? Nope. That means that we have to start in 0. For A, you say no concentrated moment. That means 0. That easy. Now, when you have this type of triangular loads, finding this distance is a little bit tricky, that distance x. So I'm going to just explain you really quick how to do it, but maybe, and just maybe, if you don't get it, it pays you go and do the method of the integrals. But just look at the reasoning that I'm going to tell you. This value is 0, correct? That value is 0. I know it's 0. I know it crosses in 0 here. And this is the shear. And we're working with areas. And I'm going to start with value of 48 and it's positive, meaning that if I'm subtracting this area, because it's negative, to that 48, whatever amount that I subtract here up to that point has to be 48, because 48 minus this area has to be 0. And this is the equation that I'm going to use. 48 minus this area. How much is this area? Well, this is x. And how much is this height here? That height is 8x, because that's the equation of the line. So 48 minus 8x times x divided by 2. That's the area of that triangle. 48, and that has to be 0. 44x squared, x equals 3.464 meters. It's basically the same because it's the same equation that we used before. Everything is related. Everything that we are doing is somehow related. Now, once we know that area, we start with the moment and say moment 0. Now, I'm going to call this point B prime. And we need this point because we say this point was important because it was going to give me a local maximum or minimum, but I didn't explain you why. Well, I explained you in class, but I didn't say it here. Remember, if we're doing the integrals, and this could be explained better when we do the integral part, we say that the shear is the integral of the load, and the moment is the integral of the shear. How do you calculate the maximum of the moment? You take the derivative of the moment and make it 0 and solve for x. What is the derivative of the moment? The shear. So I basically take my equation of shear, make it 0, and find the maximum moment. And that's why you make when the shear is 0, the moment is going to be maximum here. So let's go back here. Now I start from 0, and then I have to add this area to the moment. So it's going to be 0 plus the area of this. And this is a parabola. So if I want to calculate the area of this parabola, what I have to do is, this is going to be that is going to be 48. The area of the parabola, I don't know if you know it, but you calculate it like that. If this is a parabola, and this is B, and this is H, this area, this part, is going to be 2/3 of B times H, and this part is 1/3 of B times H. So what we have here is this, meaning that area is going to be 0 plus 2/3 of B, and B is 3.464 times H, which is 48. And that is 110.85. That value then is 110.85. But still we don't know how we're going to draw that line. Then we go back to the circle. And the circle is this one here. This shape, positive or negative? Positive. Why? Because it's plotted above the 0. Positive. Now the area, if I cut a piece here and I cut a piece here, I see that the height is getting reduced. If the height is getting reduced, first of all is positive, and the height is getting reduced is decreasing. So that means that this shape is positive decreasing. Positive decreasing is represented by this type of curve, and this type of curve is this type of curve. And you put here that this is a cubic equation. And finally, then you come to this part, and then you have to say, okay, now I have this area, and this area is going to be 110 minus this area, and that area is 1/3 of B times H, and B is 6 minus 3.464, and that should be equal to 6. When you are at this point, you have to be careful with something. When you have a triangle, and the triangle is in this shape, it's not a triangle, it's a trapezoid. This part is a trapezoid. So whatever you are getting from here is not the is not the same thing as it's come from the triangle. So this shape is coming from a rectangle on top of a triangle. So when you do the integration of this, you are not getting the parabola, an exact parabola starting from 0 like we got before. What you're getting is basically something like from the rectangle I'm going to get a triangle, and from the triangle I'm getting a parabola, something like that. I'm getting first a triangle, and then on top of that triangle I get a parabola, and this is the shape that you get. So don't expect, if you are integrating or calculating the direct area of this shape coming from a trapezoid, that is going to close in 0, because it's not going to close in 0. This part, yes, is perfect because the triangle starts only from here. So be very careful. My advice to you, this has to close in 0. It can be done. I have done it, but it doesn't work to do it. If you have a triangle in any way that you have to use a trapezoid like that, I advise you to use the method of the integrals for that. But anyway, I know this is 0 because it has to close in 0. There's no pin here. And I know this area is negative because it's plotted below the axis, and it's increasing because the height is increasing. And if I go to my circle here, and that will be for the point B, for the point B, close in 0, and the shape is negative increasing. Negative increasing is this, and because of that I close it in 0, and it closes here. And that will be the same problem made by the method of the areas. Now look at the difference in calculations. Difference in calculations. Method of the sections. Method of the sections and method of the sections. So this plus this is the method of the sections, 2 pages. Method of the integrals, 1 page. And method of the areas, 4 lines. So does that mean that you can use any method that you want to? Well, yeah, theoretically, yes, you can use any method that you want to. In real life, you have to use the method that the professor tells you to use, and you have to learn how to use all the methods. Even though this looks like a very simple problem, it's not. In the next video, stay tuned, because the next video is going to be the same triangle, or similar, but now like that, and everything changes again. So the next video that we're going to be showing is about this triangle, and see you later, guys. Enjoy your day, and I hope that you enjoyed the video. Have a good day.